Yesterday, I saw this question posted online that I thought was very interesting because it's one of those problems that really helps you improve your understanding of how to construct quantum circuits. So I decided to make a video to go over the procedure I followed to solve the problem. Now, in retrospect, the solution might look simple to some of you, but if you're really trying to improve your skills on how to implement quantum circuits, I really encourage you to pause the video and try to solve this problem yourself. So the problem says, well, given two numbers, n and m, what is a general procedure to construct the following state? So it's an equal superposition of n and m, where, the state m has an associated relative phase of e to the I beta. So the way I typically approach these problems is by starting to use some simple examples and then try to generalize from there. Now, since I already know the solution, what I want to do is start with an example that covers pretty much all of the different cases we need to look into. So let's look at the example where we have an n equal to 1, 0, 0, 0, 1, 1, 0. And m is equal to 1, 0, 1, 1, 0, 1, 1. So we're going to have to initialize a circuit with a total of 7 qubits. And here I'm going to label them from Q0 to Q6. So we have Q6, Q5, Q4, Q3, Q2, Q1, Q0. And then they're all going to start in the all zero state. And then for now, let's ignore the phase component of this m part of the state, and we'll deal with that later. So what we want to construct at this point is the equal superposition state 1 over root 2, 1, 0, 0, 0, 1, 1, 0, plus 1, 0, 1, 1, 0, 1, 1, right? So what we're going to do is, first of all, remember that we're going to label our qubits with the most significant bit to the left of the state. So our state is going to be Q6, Q5, Q4, Q3, Q2, Q1, Q0. So we're going to start working our way from the most significant qubit down. So for the first qubit, we can see that the superposition state has the exact same value. So we could actually factorize that out, right? We could just factorize that 1 tensored 1 over root 2, and then the state remaining will be 0, 0, 0, 1, 1, 0 plus 0, 1, 1, 0, 1, 1, 0, right? So that means that on Q6, to turn the state from the all zero state to having a 1 on Q6, all we need to do is then apply an X gate to Q6, right? So that's simple enough. Now, another thing to note here is that for Q5, which is the following qubit here, that's also shared as the same value for n and m. So we could actually just, factor that out as well. And since in this case, what we have is a 0, well then to Q5, we just don't need to apply any gates, right? Now for the following qubit, which is Q4, we can see now that that qubit is in a superposition of state 0 and state 1, right? So what we would need to do is apply a Hadamard gate to achieve that, right? So to Q4, we apply a Hadamard gate, and let me move this down. And if we look at what we have so far here, if we were to analyze the state we have at this point, what we have is, well, state 1, 0 tensored, and now superposition of 0 plus 1. And then for the remaining states, Q3 to Q0, we still have them in state 0, right? So tensored with 3, 2, 1, 0. So now for the next qubit, which is Q3, we can see that that one is also in an equal superposition of state 0 and state 1. So if we think about it and ignore the remaining qubits, that is like having a Bell state, right? So we have this first two qubits in state 1 and 0, and then what we want for qubits 4 and 3 is to have a Bell state of 0, 0 plus 1, 1. So to generate that, what we're going to need is just apply a CX gate between Q4 and Q3. So if we apply a CX gate here between these two qubits, now what we're going to have is, instead of here just 0 plus 1, well, we're going to have 0, 0 plus 1, 1. And then the remaining 3 qubits are still in state 0. Okay, so we've worked our way all the way down to Q3. Now let's look at Q2. So Q2 is state 1 and state 0, right? So here this is Q2 and this is Q2. So how can we accomplish that? So how can we make this qubit now be in a superposition of qubits that are opposite of what we have accomplished here so far? So what we want now is to have the state 1, 0 tensored 1 over root 2, 0, 0, but now here we want a 1 plus 1, 1, and here we want a 0. Well, if by applying a CX gate, we can get 2 qubits to be on this Bell state 0, 0 plus 1, 1, well, if we now invert the control of the qubit that is generating the superposition, that means that when that qubit is 0, so that where we have the superposition or the Hadamard gate is Q4, if we have a control gate that activates that X gate when this qubit is 0, but leaves it alone when this qubit is 1, then we can get the state that we're trying to accomplish. So for that one, what we're going to do then is place a control X gate, but where the control here gets activated when that qubit is 0. So that means that when Q4 is 0, Q2 turns into 1, and when Q4 is 1, Q2 is a 0. Now, an alternative way that is perhaps a little bit more efficient would be to apply a CX gate between Q4 and Q2, and then in Q2 just apply an X gate to invert the bits here. So we'll look into this when we start coding things up, but for now we're just going to leave this with this inverted C0 gate, which works fine. All right, and now for Q1, which is this one right here, we can see that both of those are equal to 1. So up to this point we had tensored 0, 0, but now we need to turn this qubit to a 1 in both instances. So that's easy enough, right? So to do that, all we need to do is now apply an X gate here. So then that will turn this into a 1. And then for the last qubit, we can see that it's in an equal superposition. So this is Q0, right? It's in a superposition of 0 and 1. So what do we need to do? Well, the same thing we did with Q3. We need to apply a CX gate between the qubit that is generating the superposition, so Q4, and Q0. So apply a CX gate here. And then that would turn this into a superposition of 0 and 1. So then we will, at the end of this circuit, let's actually get rid of all this. This will generate the state 1 over root 2, 1, 0, 0, 0, 1, 1, 0, plus 1, 0, 1, 1, 0, 1, 1. So let's recap the general procedure. So what we can see here is that whenever we have shared qubits that are equal to 0, all we need to do is leave those qubits alone. So that will be the case of Q5 in this example. It's the only one where we share a 0. Whenever we have shared ones, so that's Q6 and Q1, all we need to do is apply X gates. And then for the states in superposition, what we do is, well, we start looking from the most significant qubit until we reach the first one where the 2 qubits are different from each other. So in this case was Q4, right? And in that qubit, in Q4, which was the first one where we saw a superposition, we apply a Hadamard gate. And then from that point on, whenever we have a superposition where we share the same as Q4, so in this case will be Q5, which shares a 0 and shares a 1, we apply CX gates, and when the qubits are opposite, we apply CX gates, but where the control qubit gets activated when Q4 is 0 and not when Q4 is 1. So that's the general procedure. Apply X gates to share 1s, leave qubits alone on share 0s, find the first qubit that generates a superposition and apply a Hadamard gate, and then any other qubit that shares the same superposition as the qubit where the Hadamard is, apply a CX gate, and if the superposition is opposite, apply a CX gate with control 0. All right, so now we generated this state. All we have left is to implement this phase of e to the I beta, which is easy enough, right? What we can do is apply that control phase gate that gets activated whenever we find the state M. So in this case, what we will need to do is apply a phase gate where Q6 is 1, Q5 is 0, Q4 and Q3 are 1, Q2 is 0, Q1 is 1, and Q0 is 1. So this right here represents a phase gate that applies a phase of e to the I beta when these controls are met. Now, this was my original solution, but when I posted this online, someone pointed out that we really don't need to use such a complicated gate. We don't need a multi-control phase gate. As a matter of fact, if you apply a single qubit phase gate where one of the qubits in M is 1, but we have a 0 in N, then that would also apply the correct phase to the state. So what I want to do next is implement the code that generates this circuit and show how that can be done with a single phase gate instead of having to use this multi-control phase gate. All right, so now let's go ahead and implement the code that we would need to generate the circuit that creates a quantum state for an arbitrary value of n, m, and beta. So we're gonna do this in qiskit. So we're gonna do our imports first. So we're going to import numpy as np, and then from qiskit, we're going to import quantum circuit, and from qiskit quantum info, we're going to import the state vector class. All right, so the first thing we do is we assign some values to n and m, and I'm gonna do this using integer numbers. So let's say I assign 0 to n and then 4 to m. So what we need to do first is express these two numbers in the correct binary representation. Now the issue here is that if we look at, for example, the binary value for n, here in Python, it will just give us this value of 0 using 1 bit. But in the case of m, well, since we need at least 3 bits, we're going to have different number of bits for both n and m. So we need to find a way to format them in the right way. So let's first define, the total number of qubits we're going to use, which is going to be whichever is the largest value of bits used by n or m. So we're going to do max of the length of the binary representation of n and the binary representation of m. Now, if you see here in Python, we also have this prefix of 0b just to denote that this is a binary number, but our total number of qubits is just going to be whichever value is right after that prefix. So we need to subtract to this a value of 2 just to remove these two numbers. And then if we print here qubits, we're going to see that it's going to be equal to 3, which is the maximum number of bits needed to represent these two. Now we need to format these two numbers in binary. So we're going to use the numpy function binary representation and pass n and then the number of qubits, so that now n is also represented using 3 bits, and then the same for m. Now, one thing to keep in mind here is that if we look at, for example, the value of m, here we're going to represent qubits using the same way we represent bits in a binary number. So we're going to have the most significant qubit to the left. But if you think about it, to index this value, if I put the index of 0, what I get is the most significant bit, right? So I get a 1 there. And if I use the largest value in that string, so 2, I get a 0, right? So what we need to do to index things correctly so that our index matches the value of the bit in our number is we need to reverse this 2, n and m. So we're going to now express n bin as the reverse of that string. And similarly for m. So that way we can match indexes with qubit values. All right, so the next step is to create a quantum circuit with a total number of qubits equal to this variable qubits. And then what we're going to do is create a for loop to go over qubit by qubit and check if the value of n and m are equal to 0, so we don't apply any gates. N and m are equal to 1 to apply an X gate, or to check if they're different to apply a Hadamard gate or our CX gates depending on where we are in the process. So let's go ahead and create a for loop where we go from qubit 0 to the last qubit in our total number of qubits. But we're going to do this in reverse. We're going to start with the most significant qubit all the way down to the least significant qubit. So we're going to apply here a reversed function. And we're going to check if the qubit on m is equal to the qubit on m. And if they are equal, we're going to check if they're equal to 1. And if they are, well, we're going to apply an X gate to our circuit. And if they're not, well, we're not going to apply anything. So we could just ignore this else statement or just, put a pass here. Right? So let's see how our circuit looks like so far. So if we draw it just for this, well, we don't have any gates because our value of n was 0, 0, 0, and our value of m was 1, 0, 0. So in the first qubit, they're different. So we're not doing anything for that condition yet. And then the next two qubits are equal and are equal to 0, so we don't apply any gates. All right, so the next condition is if the qubits are not equal to each other, well, the first time we encounter that they're different, we need to apply a Hadamard gate. But then we don't need to apply the Hadamard in any other circumstance. So we need a flag to know if this has happened or not. So let's define a variable. Let's name it h applied and set that to false. And we also need to know which was the qubit we apply the Hadamard to, because that's going to be the control qubit for all our CX gates that are going to go to create the superpositions of all the remaining states or all the remaining qubits that are different to each other, right? So we're going to call that, let's say, h qubit, and let's initialize it to our most significant qubit, so qubits minus 1. And then what we do here is if h applied is false, so if we haven't applied that Hadamard yet, well, we're going to apply it, right, to that qubit. And then we're going to set that h qubit to the current qubit in our for loop. And then we're going to set that h applied to true, so we don't apply any more Hadamard gates after this one. All right, and if we already apply the Hadamard gate, so that's the else statement for this if statement, then what we need to do is apply CX gates between that Hadamard qubit, right, the one that created the superposition, and the current qubit. Now, here's the next condition we need to check, and is, well, we said that if the qubits are different, we need to apply a CX gate if they match what we had in the qubit that created the superposition. But if they were opposite to what we had when we created the superposition, we needed to either apply a CX gate where the control qubit gets activated when that is 0, or apply a CX gate followed by an X gate. So we need to check if the qubit in n is different than the qubit where we applied the superposition, then we need to add an additional CX gate. And that's it. That's it for the part that creates superpositions. So in this case, we are using an n of 0 and an m of 1, so it's a very trivial case. So let's just fix the code here. We forgot the equal here. So all we have here is a Hadamard gate in the most significant qubit. So let's actually go back to the example we looked into, which is for when m is equal to 70 and m is equal to 91. So that was the case where we had this superposition of 1 0 0 0 1 1 0 and 1 0 1 1 0 1 1. So let's generate that n and m, and let's generate that circuit. And here what we can see is that we have we have an X gate on qubit 6, a Hadamard gate on qubit 4, an X gate in qubit 1, then we have our CX gate between qubits 4 and qubit 3. Now, previously we had this CX gate that gets activated when this qubit is 0, but we have replaced that by a regular CX gate followed by an X gate. It generates the same type of state, and then that gets followed by a CX gate between qubit 4 and qubit 0. So we can see here that our code has generated the same circuit we had generated before, and we can double check this by creating a state vector where we pass our quantum circuit. And here we can see that we have an equal superposition of 1 0 0 0 1 1 0 and 1 0 1 1 0 1 1, which is what we expect. All right, so now all we have left is to apply the correct phase to the portion of m of this superposition state. So we said that to do that, we're only going to use one single qubit phase gate. So what we need to find is the qubit, the first qubit in which the value of m is equal to 1 and the value of n is equal to 0. So that when we apply that gate, the phase gets applied only to state m but not to state n. Now we'll have to look into a special case, and is when we don't have any condition in which m has a 1 and n has a 0. So we are going to have to invert the value of the qubit by applying X gates before and after applying the phase gate. So let's go ahead and create another for loop here, where we're going to go over again the reversed range of qubits from 0 to the value of qubits. And we're going to check if n is different than m. We're going to check if the value in m is equal to 1. Then we're going to apply a phase gate with a value of beta. We haven't defined this variable yet, so let's actually go up here, for example, and define it. So let's say beta equal to, let's say, pi over 2. And then if this condition is met, so if the two qubits are different and m is equal to 1, we don't need to continue this for loop, so we can break out of that for loop, right? So this condition will work for this particular example. So if we execute that, we will apply that phase gate in the first qubit where m is different than m and m is equal to 1. And we can see here that the right phase is being applied to m. So e to the I pi over 2, which is just applying a value of I here. But what if we have a condition where, let's say, m is all zeros, right? So let's look at that condition where, let's say, we have a superposition of 15 and 0. So in this case, we needed to apply a phase to the state 0 0 0 0, but it didn't get applied, right? So what we need to check is, well, if n is different than m, but now we have a condition where m is not equal to 1. So we have an else here where we need to identify which was the qubit where that was different. So we're going to store that in some variable phase qubit, and let's actually initialize that here to the most significant qubit. And we also need a flag to know if the phase was applied or not. So let's set that to false. So if this for loop goes through every single qubit and this condition is not met, so this phase gate wasn't applied, we'll store which was the qubit where we encountered the first difference between n and m. And what we're going to do is, if we did not apply the phase gate, we'll then apply first an X gate to that phase qubit we stored, then apply our phase gate with a phase of beta, and then another X gate. And if we do that, then now our phase gate is being applied to the correct qubit. And here we can see that now that state of 0, 0, 0 is getting that phase that we need. So that's it. That's how we generate that additional phase using only one phase gate. And you know, one of these two conditions will always be met. So we will always have a qubit where n is different than m, because otherwise n, the whole value of n, will be equal to the whole value of m, which never happens because we wouldn't have a superposition. So I really had a good time solving this problem. I hope that you found it useful, and let me know if you have any questions.